Good morning, everybody. I welcome you all to my series of lectures on the concept of magnetically coupled circuits. So, I have divided my lecture on magnetically coupled circuits into four parts. The first part on magnetically coupled circuits, I will discuss regarding Faraday's law of electromagnetic induction, Lenz's law, the concept of self-inductance, mutual inductance, coefficient of coupling, and derive the relation between these three concepts. The second part of my lecture on magnetically coupled circuit will contain the concept of dot convention, how to find electrical equivalent of magnetically coupled circuit, and how to write KVL equations for magnetically coupled circuit. Third part and fourth part of my lecture on magnetically coupled circuits will contain how to find equivalent inductance of magnetically coupled circuits and various tutorials on the concept of magnetically coupled circuits. So first let us see what is Faraday's law of electromagnetic induction. The first law states that whenever a coil or conductor cuts the magnetic field, an EMF is induced in that coil or conductor. It can also be stated in other words as whenever a flux linking the coil or conductor changes, an EMF is induced in the coil or conductor. The second law states that the magnitude of this induced EMF is equal to the rate of change of flux linkages. So here is a small illustration of Faraday's law. I have a coil connected to a galvanometer with a bulb indicator and a bar magnet. When north pole is brought towards the coil, you can see due to the change in flux, it deflects in one direction, and when the south pole is brought towards the coil, you can see it deflects in another direction. So depending upon the velocity of the bar magnet movement, the deflection in the galvanometer will be proportional. When you bring this bar magnet towards the coil at a very slow rate, the deflection will be very slow. When it is brought at a very faster rate, the deflection in the galvanometer will also be at a faster rate. The direction of induced EMF can be given by Lenz's law and Fleming's right-hand rule. Lenz's law states that the direction of induced EMF will be in such a way so as to oppose the very cause that is producing it. So this is a small illustration of Lenz's law. I have a bar magnet, I have a coil with a galvanometer and bulb indicator. So when the bar magnet is slowly moved towards the coil, it will induce an EMF, and this EMF will induce a current in such a direction so as to oppose this movement. Hence, it is producing a north pole which will repel the movement of the bar magnet. So hence the deflection of the galvanometer will be in one direction. Similarly, as you can see that if the bar magnet is in stationary, this will not have any change in magnetic flux, hence it is no deflection galvanometer. When the bar magnet is moved away from the coil, it will induce an EMF, and this EMF will set up a current in a direction so as to oppose this movement of bar magnet away from the coil. Hence it will produce a south pole which will attract the bar magnet, and the deflection in the galvanometer will be in another direction. So hence we can conclude that the current setup is in such a way so as to oppose the movement of bar magnet. Fleming's right hand rule. So Fleming's right hand rule, the thumb indicates the motion of the conductor, the forefinger indicates the direction of magnetic field, and the middle finger indicates the direction of the current induced in the coil or conductor. Expression for induced EMF. So as we have considered a coil, let us consider it has n turns, and initial flux let us assume to be phi1 Weber, and final flux let us assume to be phi2 Weber, and this change let us assume to be occurring in t seconds. So according to second law of Faraday, E is equal to N into d phi by dt. That is, the direction of induced EMF is directly proportional to rate of change of flux linkages. So according to Lenz's law, this induced EMF that is set up will induce a current, as we have seen, in a direction so as to oppose the cause producing it. So the negative sign in the expression indicates that it is opposition to the cause that is producing due to Lenz's law. The nature of induced EMF that is occurring in a conductor or coil are two types. One is statically induced EMF and second one is dynamically induced EMF. So as the name indicates, statically induced EMF. Static means stationary, dynamic means when it is in motion. So the basic difference between statically induced EMF and dynamically induced EMF is the dynamically induced EMF occurs when the conductor is in motion and the magnetic field is in stationary. So the EMF that is induced in such a way, that is when the conductor is in motion and the magnetic field is in stationary, in this way the EMF that is induced in the conductor is called dynamically induced EMF. Obviously the statically induced EMF is nothing but here the conductor is stationary whereas the magnetic field is in motion. So this induced EMF that occurs when conductor is stationary and magnetic field is in motion is called statically induced EMF. So statically induced EMF is of two types. One is self-induced EMF and second one is mutually induced EMF. So our main concentration will be on statically induced EMF rather than dynamically induced EMF. So first, self-induced EMF. Let us consider a coil which has turns N and is connected in series with a battery E and a variable rheostat R and a switch S. So as soon as we close the switch, current starts flowing I in the coil, and as soon as the current starts flowing, it will produce a flux, some phi, let us assume, and this flux will link the entire coil. So the total flux linkages of this coil will be nothing but N into phi, where phi is the flux produced in the coil. So now using the variable rheostat, I will change the current that is flowing in the coil. So as soon as the current changes, the flux that is associated with the current will also change. So due to the change in the flux linkages, that is N into phi, will also change. So according to Faraday's law, when there is a flux change in flux linkage, EMF is induced in the coil. So this EMF that is induced in the same coil. So the reason why the EMF is induced is due to change in its own flux. So the EMF that is induced in the coil due to change in its own flux linking the coil is called self-induced EMF. So this self-induced EMF direction can be given by Lenz's law. So self-inductance. So what is self-inductance? So if the current flowing in the circuit or in the coil is either increased or decreased, so depending upon the change in current, it will set up a EMF in a direction so as to oppose the cause producing it. So if I increase the current in the coil, the EMF is set in such a way so as to oppose this increase in current. Similarly, if the current in the coil is decreased, self-induced EMF will be set up in a direction so as to oppose this decrease in current. So therefore, this is nothing but the property of an inductor. As we know, the inductor opposes the change in current. So this property of inductor, that is opposing any changes in current, is called self-inductance. Here we should note that the self-inductance does not prevent the current from changing, but only it is delaying the change. Expression for self-inductance. So from Faraday's law of electromagnetic induction, E is directly proportional to N into d phi by dt. So the negative symbol indicates that it is opposing the change in current. So this expression I can modify as E is directly proportional to d by dt of N into phi. So here I have neglected the negative symbol. So let me consider this as the first equation. So we all know that the change in flux occurs due to the change in current. So whenever the current changes, the flux linkages, that is N into phi, also changes. So in other words, I can tell that E is directly proportional to di by dt, because when there is a rate of change of current, then also EMF is induced. So if I remove the proportionality symbol, I can write it as a constant into di by dt. This constant is called inductance, which is represented by capital L. So E is equal to L into di by dt. This I can write as d by dt into Li. I'll consider this as second equation. You can clearly observe that the first equation as well as second equation are both similar. The first equation is E is proportional to d by dt of n phi, and the second equation E is proportional to d by dt of L into I. So I'll equate these two equations. So we'll get an expression, that is Li is equal to n into phi. That is, from that L is equal to n phi by I. So from this expression of self-inductance, we can define self-inductance as, it is nothing but the flux linkages per unit ampere current. Its Henrys is the unit of self-inductance. So the other expressions we can also derive for self-inductance. So we all know from the concept of magnetic circuits that flux is equal to mmf by reluctance. So flux phi, as you can see, is mmf. We know that it is n into I, and reluctance is nothing but S. So I substitute this expression in the above expression, L is equal to n phi by I. So after substitution, we will get L is equal to n square by S. So this is another expression for self-inductance. But we also know that reluctance S is equal to L by mu A, where L is the length and A is the area of cross section. So substituting this in the above expression, we'll get another expression for self-inductance, that is L is equal to n square mu A by L, where mu I can write as mu naught into mu R. So these are the two other expressions for self-inductances. Mutually induced EMF. Let me consider two coils, coil A and coil B. Coil B is connected to a galvanometer G, and coil A is connected to a battery in series with a rheostat and switch. So as soon as I close this switch, current starts flowing in coil A. So due to this current, flux is produced phi 1. So this flux will link both coil A as well as coil B. So this flux is the total flux that is produced, and out of this total flux, a part of the flux that is connecting or linking coil B is called mutual flux, which are represented by phi 12. Phi 12 indicates flux produced by first coil, which is linking second coil. So now let me change the current flowing in coil A. So as soon as I change the current in coil A, the flux that is produced, that is phi 1, will change. So as soon as phi 1 will change, obviously phi 12 also changes. So due to the change in flux that is linking both coil A and coil B, according to Faraday's law, EMF should be induced in both the coils. So the EMF that is induced in coil A due to the change in flux in coil A is called self-induced EMF, and the EMF that is induced in coil B due to the change in flux of coil A is called mutually induced EMF. So the flux produced by one coil is getting linked with another coil, and due to the change in this flux produced by first coil, EMF is induced in second coil. So this induced EMF, we call it as mutually induced EMF. Mutual inductance. So as we have seen that any change in current in coil A is accompanied by a mutually induced EMF in coil B. That is, if I change the current in coil A, it is inducing an EMF in coil B. Similarly, if I change any current in coil B, it also will induce a mutually induced EMF in coil A. So this property, that is the property of two adjacent coils to induce voltage in one coil due to the change in current in another coil, is called mutual inductance. Expression for mutual inductance. So in the same example, let us consider the current in coil A to be I1, the current in coil B to be I2, the number of turns to be N1 and N2 respectively. So in this case, phi12 is the mutual flux, which indicates the flux produced by first coil, which is linking second coil. Similarly, if this arrangement is changed from coil A to coil B, then we'll get a mutual flux as phi21. So phi21 is the flux produced by second coil, which is linking first coil. So the induced EMF in coil B is due to the current change in current in coil A. So this I can mathematically express as the mutually induced EMF in coil B is directly proportional to rate of change of the mutual flux, that is phi12. So if I remove the proportionality symbol, I'll get a constant, that is N2. So this I can rewrite as EM2, mutually induced EMF in coil B is nothing but d by dt of N2 into phi12. I have assumed to be first equation. So as you know that the change in flux linkage is directly proportional to change in current. So the induced EMF in coil B is directly proportional to rate of change of current in coil 1. So this proportional symbol, when I remove, I'll get a constant to be M. So EMB, mutually induced EMF in coil B, is nothing but M into di1 by dt. This I can rewrite as EMB is equal to d by dt of M into I1. This I'll consider as second equation. So since the expressions for 1 and 2 are same, I'll equate both the equations. So on equating, I'll get M is equal to N2 phi12 by I1. So this is the expression for mutual inductance. So this is when the coil A is connected to the battery and rheostat, and the coil B is connected to the galvanometer. Now let us interchange the positions. So in coil B, let me consider coil B to be connected to a battery rheostat and coil A is connected to a galvanometer. So in previous case, we have got the expression of M to be N2 phi12 by I1, where N2 is the number of turns of second coil, phi12 is the mutual flux, and I1 is the current flowing in first coil. So in the similar manner, if I try to derive the expression for the second case, I'll get M is equal to N1 phi21 by I2. Here N1 is the number of turns of first coil, phi21 is the mutual flux, and I2 is the current flowing in the second coil. So What are the other expressions for mutual inductance? We all know that mutual flux is equal to mmf by reluctance. So mmf is nothing but product of number of turns into the current flowing. So which is N1 into I1 by reluctance is nothing but L by mu naught mu R into A. So if I rearrange these terms, I'll get N1 N I1 mu naught mu R A by L. So M, as we know, is N2 into phi12 by I1. So I'll substitute this in this expression. I'll get an expression for M, which is N1 N2 mu naught mu R A by L. So where N1 N2, here if I bring this term to denominator, it is nothing but L by mu naught mu R into A, which is nothing but reluctance. So M is equal to product of the number of turns of the two coils divided by reluctance of the coil. Coefficient of coupling. So coefficient of coupling is nothing but the fraction of the total flux that links the coil. So as we have seen in previous example, that if phi1 is the total flux produced, out of this phi1, phi12, the mutual flux is linking the other coil. So that fraction, that is out of phi1, phi12 is linking the second coil. Out of phi2, phi21 is linking the other coil. So this fraction of the total flux that is linking the other coils are called coefficient of coupling. So mathematically we can write K is phi12 by phi1 or phi21 by phi2, where phi1 is the total flux in first coil, phi2 is the total flux in second coil, and phi12 and phi21 are mutual fluxes. So as we know that phi12 will never be greater than phi1, similarly phi21 is never greater than phi2. So from this expression we can conclude that the maximum value of K can be 1, it will never cross 1. Relation between self-inductance, mutual inductance and coefficient of coupling. So let us derive what is the relation between these three terms. So from the above expressions which we have obtained from previous analysis, M is equal to N2 phi21 by I2 and M is equal to N1 phi12 by I1. So these we have obtained in previous analysis. Now I'll multiply both the equations. I'll get M square is equal to N1 N2 into phi12 by I1 into phi21 by I2. So this I can write as, so from the expression of coefficient of coupling phi12 I can replace as K into phi1 and phi21 I can replace as K into phi2. So when I replace them, I'll get M square is equal to K square N1 N2 phi1 phi2 by I1 I2. This I can write as, I can split this as K square into N1 phi1 by I1 and N2 phi2 by I2. N1 phi1 by I1 is nothing but L1, N2 phi2 by I2 is nothing but L2. So M square is equal to K square into L1 L2, thereby M is equal to K into root over L1 L2. So this is the relation between mutual inductance, self-inductance and coefficient of coupling. This concludes my lecture on the first part of magnetically coupled circuits. In my next lecture on the magnetically coupled circuits, I will discuss the concept of dot convention. Thank you.